Okay, sorry, the video accidentally got cut off, and I'm not editing these because I don't really have time to, so they're just straight through recordings. So part B of number 8 is going to be on a separate video, which you already know because you're now at that separate video. Okay, so part B of number 8, I'm sorry, part C rather. Part C of number 8 is asking us to find the Fourier series coefficients of the periodic signal Zn, and Zn is summation of shifted delta functions. So n naught is given to us as 2, and from there we can find the angular frequency omega naught as just equal to pi. This is actually an unnecessary step, but it's just a good habit to be in, because in a lot of problems you probably will need it. Okay, so the Fourier coefficients, we're going to use the formal definition, and that's just given as 1 over n, and in this case n is 2, and it's going to be from it, the way they write it is n equals n, so this just means from 0 to 2. And we'll select n here. Okay, so remember that this is how you would normally write it: x of n e minus j k omega naught n. Okay, so the subtlety here is that x of n itself is an infinite series, so the way to write this is n equals 0 to e minus j k omega naught n k equals minus let's not do it that way. Okay, so probably for a lot of you, this might actually be the first time you've seen something like this, a product of sums, that is. And there are some ways we can handle these algebraically, but we don't really need to think about that now. The easiest way to do this is to realize that this inside summation right here, so we're iterating through k, so we get this infinite summation of shifted delta functions, and for negative values of k, we're going to get delta functions that are shifted leftward. So let's say, since we can't start at negative infinity, we'll say 100. So these are all the preceding terms, so like delta n plus 200 times E minus, no, plus, because they cancel, 100 omega naught n. And then it keeps going, and eventually we'll get to k equals 0, and that's delta n times E 0, and then delta, we'll get to k equals 1, and then these signals get shifted rightward. And we get E minus J 2 omega naught n, and that continues on. Okay, so, sorry. This is not 2, this is 1, because our summation is 2 iterations long, so the 0th term is the first one, and the k equals 1 term is the second one. So be careful here, because there's plenty of places you can make mistakes at, and small mistakes crash rockets into planets, so we want to avoid those. Okay, so now we have this infinite summation of shifted deltas, and this summation right here is from n equals 0 to 1. So remember the definition of the delta function is equal to 1 for n equals 0 and 0 for all other values. So we basically, the way this summation runs is we put in n equals 0 in each of these terms, and we would theoretically write them down if you were on a computer. You can't do infinite terms, but you can do a lot. And then you would go to the n equals 1 term and add those to all these ones. So the way we need to solve this is by realizing that, say, n equals 0, say we put it here, we get delta 200. Well, that's 0, because delta 200 is, from the definition right here, just 0. The only time delta is 1 is at n equals 0. So we come here and, okay, this term is equal to E0, and E0 is equal to 1. Okay, that's something, that's a non-zero term. And then we want to look here, which is the next term in the summation, dn minus 2, well, we put n equals 0 here, we get d minus 2. Well, that's 0. Okay, so the next time, we're going to write this down, ak equals 1/2, and we said the only term we got out of there was when we get d0, so E0. Okay, so now n equals 1. Well, this is just 201 then, and that's still 0. And could write here just to prove to you conclusively, if we were at the k equals -1 term here, you would get dn plus 2, and that would be the term before the dn term. So we can see that when we put n equals 1 here and you go through and look, you're never going to find a situation where you get d0, that condition being the one where the delta function is equal to 1. So for the n equals 1 iteration, there aren't any terms in this summation here that resolve to non-zero. So the Fourier coefficient is the Fourier series coefficients in total is just 1/2. And that would be the A0 term, because when we did it up here, that was k equals 0. So there you go. There's some nuances in that argument, so think it through yourself, and I'll see you in the next problem. Bye.